Part C, find the expected value of x and the variance of x. I think it is worth reminding you here, without looking, that if x is binomial with parameters n and p, and by the way, what I'm writing right now is the first time I've written this, is standard kind of notation, shorthand notation to say x is binomial with parameters n and p. I'm writing this down for the very first time. I will write it down in the future. It might be worth you writing down. This means it's shorthand. X is or has a distribution is what this little squiggle means. Doesn't mean it's equal. As distribution might be the best thing to call it. Binomial, B means binomial, parameters n and p, n being the number of trials, p being the number of the probability of success on each trial, independent and identical trials that are either success or failure, Bernoulli trials. X is counting the number of successes. If x has that distribution, the expected value of x is n times p. That's a very intuitive kind of formula. That's not the definition of expected value, right? The definition of expected value is that it's the sum of x times little f of x, right? But that sum, when x is binomial, happens to equal n times p. We derived this last time with the moment generating function. And this makes good intuitive sense. If I'm a 40% free throw shooter and I do 10 attempts, probability of success 0.4, 10 times 0.4 is 4. I would expect to make close to 4 of my free throws. If n is 100, if I'm trying 100 of them, 0.4 times 100 is 40. Of course, there's complications in real life. If I'm trying 100 free throws, I'm going to get tired. By the 74th free throw, I'm like, oh, I don't feel like doing this anymore. Right? So my probability of success might go down because of that, because I'm getting tired. But for the purposes of modeling and ignoring things like getting tired, getting sleepy, wilting under pressure, this is a simplifying assumption to assume P stays constant. Probability, I think, is the most ideal math subject for mathematical modeling. I love differential equations, for example, but I think probability is even more useful in general for most people for mathematical modeling. For your average person, even on or in a regular job, probability is certainly more useful than most people would not need differential equations. That's the expected value of x. What about the variance of x? This is less intuitive, but still true. It's n times p times 1 minus p. N times p times q, if q is 1 minus p. These are things worth remembering, even though you technically can either put them on your note card, or again, you really don't have to, because I'm gonna provide the table for you at the exam. And this also means the standard deviation is the square root of the variance is the square root of n times p times 1 minus p. Square root of n times p times q. That's something you can write down as well. You can find the second moment using the moment generating function and confirm the variance that way as well. Okay, what I really wanted to focus on is E through F here. Let's focus on a couple things in F. I want to focus on these two. Probability that x is between 2 and 7 inclusive, and the probability that x is between 2 and 7, possibly including 2, but not 7. You've had some problems where you had to think about this kind of thing before. But let's emphasize something here. I'm going to use parentheses instead of square brackets. Let's do the first one. Probability that x is between 2 and 7 here, when x is binomial with n equal to 15 and p equal to 0.2. We want to relate this to the CDF. That's what you should have realized. Cumulative distribution function, the capital F. But it's a little tricky with discrete random variables. It's actually easier with continuous random variables. You've got this event in here. it's helpful to relate this to a couple other events. It's helpful to think of the event that x is between 0 and 7 as a union of mutually exclusive events that x is between 0 and 1 union the event that x is between 2 and 7. Now, the notation I'm using here is not good, but it's convenient. I'm using curly braces as if these are sets, and in a sense they are in my mind, but this is not a typical way of describing sets. I'm using the curly braces to emphasize in my mind that events are sets. And so when I write this, I'm sort of thinking of this as being the set of all x. The event that I'm thinking of this as being the event that x is between 0 and 7. I suppose I could try to use more standard set builder notation and put an x over here with a vertical line. But it's a little bit misleading to write that, because capital X is a random variable. It's not really a number. It's an abstract idea that really, I said, in grad school becomes a function. We don't think of it as a function here. Like if you look up probability theory on Wikipedia, you'll see what I mean, how grad school level probability theory is like, it's kind of scary looking. Random variables actually become functions. And there's all sorts of other weird stuff that you'll see there. We're not being extra precise about that. We're not being extra picky, and I'm not being extra picky about the notation here. I'm just thinking of this, okay, that's the event that x takes on a value between 0 and 7. This is the event that x takes on a value between 0 and 1. This is the event that x takes on a value between 2 and 7. What about the event that x is strictly between 1 and 2? Can't happen here because x is discrete with whole number values. So I don't need another set in here representing x being strictly between 1 and 2. This is based on x being discrete with whole number values. And these are mutually exclusive events. These two things, mutually exclusive. So, axiom 3 of probability, the addition rule for mutually exclusive events, would say that the probability that this event occurs, which now will not write curly braces for, is the sum of the probabilities of these other two events. Meaning the probability that I'm interested in is a difference. Subtract this from both sides. So the probability of x being between 2 and 7 is the probability of x being between 0 and 7 inclusive minus the probability of x being between 0 and 1 inclusive. But those probabilities, because x can't take on negative values, being binomial, it's got to start with 0, are CDF values. This is capital F of 7 minus capital F of 1. Not capital F of 7 minus capital F of 2, as would be the case if this were a continuous random variable and we'd be doing an integral and using the fundamental theorem of calculus. This is supposed to hint at the fundamental theorem of calculus for integrals without actually being the fundamental theorem of calculus. There's no integrals, and well, the 2 changes into a 1. I could have thought of this event here, this inequality there, I could have thought that as being less than 2, strictly less than 2. And because x is discrete, taking on whole number of values, that's the same as the event as x being less than or equal to 1. And it's almost like you would have had a 2 here, but not quite. Again, x is discrete. So this is the calculation you should have done. with the table, that you do want to get a little practice with the table. Make sure you could do it in the book. Otherwise, with technology, distribution menu, binomial CDF, it's capital F. For this situation, N was 15, P was 0.2, capital F of 7 is about 0.99576. That's your probability of getting less than or equal to 7 for X. Right, 7 and 15 trials, 20% chance of success. On average, you're going to have 3 successes in 15 trials. So your probability of being less than or equal to 7 successes should be close to 1, and it is. And for the other one, we just changed the 7 to a 1. Minus 0.16713. Should have gotten about 0.8286. Let's round to 1 fewer place of accuracy there. If I change this problem, I guess I'm not going to do the exact one that's in the book. If I change the first inequality to being a strict less than instead of a less than or equal to, this is equivalent in this situation to 3 being less than or equal to X with a less than or equal to sign. And I could think of it ultimately as this difference. Whereas up here, the 2 change to a 1, so to speak. Down here, because it's a strict less than, this 2 stays a 2 because it's the same as it being a 3 changing to a 2. Tricky, tricky, tricky. You got to be really careful. So this becomes capital F of 7 minus capital F of 2. So it's kind of like the fundamental theorem of calculus works in this kind of situation. If this first inequality is a strict less than, and the second inequality is a less than or equal to. Moral of the story, you got to be careful when X is discrete and you're doing these things.